Start today by talking about something we have ignored. We have not talked about Newton's third law, and we probably should. So you guys already know Newton's third law, and what I mean by that is you've had a colloquialism about Newton's third law for quite some time. So I want to talk to you a little bit about the colloquialism and how it is not the law, and then explain to you what the law actually is. The colloquialism is, for every action, there's an equal and opposite reaction. You guys heard that before? Yeah. That's the colloquial Newton's third law. There are bits of truth in there, and lots missing. And it doesn't state what it's supposed to state. So allow me to state the law as you should know it. For every force, there's an equal and opposite reactive force. I'm not going to write this down. You should. For every force, there's an equal and opposite reactive force. Now, I don't use the word every lightly here. When a law says something like all, every, total, you should be careful. It's hard to have a law that has no exceptions. This has no exceptions. For every force, there is an equal and opposite reactive force. So every time you've drawn a free body diagram, for every one arrow you've drawn, somewhere else in the universe is an arrow pointing back. That's what I'm really trying to get you to understand. You might not know where that other force is, but for every force, there's an equal but opposite reactive force. Another way to say that is that all forces come in action-reaction pairs. All forces come in action-reaction pairs. Today, from this day forwards, it's your job to figure out what those pairs are. But here is a small little detail that's not in the law, but should be. These forces act on separate objects. These forces act on separate objects. The action-reaction pair can't be on the same object. These forces act on separate objects. So let's start with an example that may illustrate this a small amount. And I want to start with something for which you are already familiar. So let's say that I am pulling this box with a force in this direction. And let's say it's sliding across this surface at a constant velocity. Draw the free body diagram for the forces acting on this box. Draw it right on the box. So I understand that this one should have been easy for you. So Leah, give me a force that's acting here.
Wait.
Okay, so I assume you drew a downwards arrow. Okay. Excellent. Mia, give me another force acting on this. Which one? Normal force. How'd you draw it? Straight up. I wouldn't draw it as big as the weight because I also know that applied force is pulling upwards a little bit. So Cameron, can you give me another one?
Friction.
How would I draw it?
The left.
Okay.
Okay.
I would say these are probably not in good proportion, but this will do for this discussion. Now, Newton's third law. We've drawn these four forces here. For every force, there must be an equal and opposite reactive force, which means for these four arrows, there are four other arrows someplace else in the universe. that are the reactive forces. I'll help you out with a little bit. We didn't talk about this, but the table itself, it's that this box is on. I mean, I don't know if it's a table or not, but let's assume that the surface is a table. If we make that assumption, then we can probably imagine that if the box is resting on the table and pushing up on the box, then it's probably not a hard stretch to imagine that the table is receiving a force from the box that is downwards. Right? You can imagine somebody has sat on you before. You have experienced their downward force on you while you provided an upward force on them. That was a Newton's third law pair. The thing about the Newton's third law pair is they act on different objects, but they're equal and opposite. So the box presses down on the table with the same amount of force as the table presses up on the box. That's a Newton's third law pair. This normal force right here doesn't affect the box. It affects the table. That's important, I think. Now, this one's going to be harder, and I'm going to do this one too. I want to talk to you about it because I think you won't know this. But there's a Newton's third law pair for the frictional force. If the box scrapes along the table, then the table is scraping against the box. So although the table is trying to prevent the box from going forwards, the box is trying to cause the table to go forwards. If the table were on a slick surface, you can imagine pulling the box might start dragging the table along with it. Can you imagine that? I hope so. You're going to have to. That is a Newton's third law pair. Now, the applied force. We've just made this some disembodied person in the past, but there had to be somebody who was pulling on the box. I said that I pulled on the box. Therefore, the box is also pulling back on me with an equal and opposite force. If you've tried to pull something, especially something heavy, you have often felt like it's pulled you. It has. You pull on the box pulls on me. These forces don't cancel out, by the way. Some people think these forces cancel out. They don't. They act on different objects. This force acts on me. Now, either I am pulled forwards, or there's enough friction between me and the ground to keep me from being pulled forwards. If you've pulled on something heavy, you know that sometimes your body tends to be pulled. That's what happens. Because there's a force acting on you. Of course, we're taking this not to an extreme, we're taking this to reality. That at some point or another, you have to consider the gravitational force. And if the Earth pulls down on the box, then the box pulls up on the Earth. That pair exists too. Again, the force on the Earth is separate from the force on the box. You'll hear me say this more and more now that we're beginning to discuss Newton's third law, that the effectiveness of a force depends on the inertia of the object. The box is pulling up on the Earth, and the Earth is pulling down on the box. It's the same size force. But that force is more effective at moving the box than it is at moving the Earth. Why? The Earth has a lot of inertia. The box doesn't. The effectiveness of a force will depend on the inertia of the object. So there is a Newton's third law pair between the box and the Earth. It's just that the effect of the box on the Earth isn't very great. But the effect of the Earth on the box, well, that's pretty big. Newton's third law, for every force, there is an equal and opposite reactive force. Now, we have to kind of show how we're going to do this. How does this manifest itself in our class? So I'm going to do, I did a problem in first period. I've decided I won't do as a starting problem for you guys. I'll make it your second problem. Your first problem is going to be a little more straightforward. I want you to imagine two boxes resting on a frictionless surface. So I have a 5 kilogram box and a 15 kilogram box. And somebody pushes on the first box with 100 Newton force. Let's assume this is a frictionless surface. So we're going to try and make this as simple as possible. I would like to know the acceleration of the system and the force between the boxes. Okay. Now, this is a multi-body problem. Therefore, we have to use multi-body rules to solve it. Those rules are not much different than what you already know, but we have to adjust your force rules just a small amount. Here's the adjustment. The first adjustment begins at the start of the problem. You need to figure out how the motion of one object is connected to the motion of the others. If it's a multi-body problem, then more than one object is going to be moving. You need to figure out how the motion of one object is connected to the motion of the other. This should be simple, but you need to be thoughtful about it. Again, in a multi-body problem, you need to consider how the motion of one object is connected to the motion of the others. So, in this problem, can we agree that the only way the 5 kilogram box moves to the right is that the 15 kilogram box moves to the right?
Yes.
That's a good, so start talking displacement first. Then maybe move on to direction, right? They're both going to have to move to the right. If I push on the 5 kilogram box, I don't think the 15 kilogram box moves to the left or down or side, up or up, right? It's going to move to the right as well. Now you have to get a little more particular. If the 5 kilogram box moves 1 meter, does the 15 kilogram box move 1 meter?
Yeah.
That's not unreasonable. If the 5 kilogram box moved more than the 15 kilogram box, then the 5 kilogram box is being pushed through the 15 kilogram box, right?
Yeah.
Assuming that doesn't happen, the motion of one seems to be directly connected to the other. Do you understand? I'm having a conversation. These are the questions you should ask yourself. How does the motion of one object affect the motion of the other? And go through things like displacement, velocity, and land on acceleration. That's the most important part. You want to know if their accelerations are the same or connected. That's what you need to land on. That's the most important thing I'm saying here. That's the part where you get your pencil moving. You need to figure out if the acceleration of one object is the same as the other. In this case, they're not only the same, but in the same direction. I believe this system will accelerate this way. So, question number 1, how is the motion of one object connected to the motion of the other? Question number 2, it's not really a question, it's a request. Create a common direction for positive for both objects. This is different than how your book does it. So if you want a different address, look at your book. I don't like the way the book does it. I'm going to do it this way. So I'll say it again. Choose a common direction for positive for both objects. I am choosing to the right to be positive for both objects. Look, in this problem, this one's a ridiculously simple starting point. I started with a little more complex one in first period. We're going to start a little more simply. That way, these choices will make more sense. So, once I've done those two things, identified how the boxes move together, and identified a common direction that I will call positive, now you go through your set of steps. You do it individually, meaning I'm going to do the steps for the 5 kilogram box by itself, and the steps for the 15 kilogram box by itself. This part should not be hard. You should know how to do this. So I'll let you to it. You should draw the arrows. This one should be easy. You're going to make mistakes. I'm okay with that. You get 60 seconds. Some of this should have been easy. Hopefully it was. So, 50. Are we in agreement? Normal. $100 newtons. Those are the easy ones. Normal from 15. Right? Would you agree that there is two surfaces in contact with the box? It's in contact with the surface that is the floor, and it's in contact with the surface that is the other box. Two normal forces. I'm saying it's normal from the 15 kilogram box. I'm labeling it that way so that I know where it's coming from. I know it acts on the 5 kilogram box. If these boxes were labeled M1 and M2, I'd probably label this N2. Now the green box. 150 newtons downwards. Normal force upwards. I know some of you put 100 Newton force acting to the right on this box, but you shouldn't have. That 100 Newtons is not acting on this box. There is a normal force from the 5 kilogram box acting this way, but that's it. That should be the only forces on this box. The 100 Newtons that's over here acts only on this box. It doesn't act on the other box. So draw it the other way is a problem. So you can only go through your list of steps as you've identified them. So if the 100 newtons isn't touching the 15 kilogram box, it doesn't apply to it. Any questions about this? You have more. You should have put a coordinate system here. I'm only going to worry about the x direction. I don't have to worry about the y direction. Right? The y direction's balanced on both of them. But I am going to purposely make this the positive x direction on both. Because that was the agreed upon positive direction. We said that from the very beginning. Make an agreed upon positive direction that you apply equally to both objects. That's what we've done. Now, you have to insert something new here. We didn't ask yet whether this is a first law problem or a second law problem, but I think you probably know that this is going to be a second law problem, especially since you were asked to find the acceleration of the system. That seems to kind of be obvious. But you do have to do something else, something that you perhaps haven't thought about, that's new, that applies to the multi-body problem only. You have to go through and find the Newton third law pairs. You have to find how one object is connected to the other. Which is the forces that are equal and opposite? They're easy to find because they are the things that connect the two objects together. In this case, it's a normal force that connects the two objects together. Those two forces must be equal and opposite. Once you have decided what the equal and opposite forces are, name them the same thing. So I'm just going to name them N2 to separate them from the other force. N2. Eventually, once you realize where your Newton's third law forces are going to be, you'll probably be able to do that on the fly when you're drawing your diagrams. But you should always stop and make sure you know what is connecting your two objects together. This problem is stupid obvious. They won't all be. Now, the rest of this progresses just like before. Sum of forces equals MA. You should do that. You should know how to do that by now. You've taken a test on it and done remarkably okay. So go forwards. Apply Newton's second law. Should be easy. All right, I'm done. So if you're taking more time than that, I'm not sure what you're doing. 100 minus N2 equals 5A. I plugged in the mass. There's a force to the right. I said 100. Force to the left, I called N2. Not to be confused with N. The other box is only experiencing one force to the right, N2. When you are done, you should have formulas that could be used to solve your problem. Do you? Do you have a formula that could be used to solve your problem? So I should be able to pick on two of you. You've got, I'll say 60 seconds to be able to figure out what the acceleration and the normal force are. I will choose two people to explain to me what the normal force and acceleration are. Andy, can you tell me what the acceleration is? I don't think it's 10. Yes, ma'am. What's that? I think it's 5. Can you tell me how you got that? Excellent. Yes, I think that's how it goes. Now that you have that, finding N2 should be pretty easy, right? You have two places to try it out. I think the easiest one would be here. Don't you? N2, what was it, 125? What is 15 times 5? 75, right? Is that right? 75 newtons? Now, this is the force between the two boxes. It should be in newtons. I don't think this is terribly tough, but ask yourself a simple question here. If this force had been on the other side, do you think it would have been 75 newtons between the boxes? Some of you have an intuitive sense about this and some of you don't. But if I pushed in the other direction, do you think the acceleration would change? Same force, same inertia. You might not see it this way, but if I pushed this way with 100 newtons of force instead, the whole system has a mass of 20 kilograms. You might not see it this way, but we could have cut out the middleman in this problem and did net force on the system was 100 equals 20A. We could have done that from the beginning. The whole system has a mass of 20. That's kind of what ended up happening, right? If you look here, this is 100 equals 15A plus 5A. Or 100 equals 15 plus 5 times A. Isn't this the mass of the system? Every time you do a multibody problem, you will end up with this. Some force times the mass of the whole system. If you don't, you did something wrong. I guarantee this will show up every time. That's how you know you've done it right. If you somewhere along the road have to add up all the masses in your system, you've done it right. It's the only way these problems work because all of these objects have inertia. So at some point or another, the inertia of the system shows up. Now I'm saying that because You may not see it this way, but if I push on the other box, I bet the force between these two is less. I know that because I used to load trucks when I was a kid in summertime between colleges. And I would push boxes across the floor. They were cabinet boxes. They were as big as me. So I know you don't push on the small box and have another box that's bigger behind it. You push on the big box with a small box behind it. You have a chance of crushing little boxes that get stuck in between here if you do it this way, because the force is higher. You should try this problem again. You'll find that the force between the two boxes is 25 newtons. You should prove it to yourself. And I know it's 25 newtons for a number of reasons. There's a total of 100 newtons. 25 of those newtons were used to push the 5 kilogram box, and 75 of those newtons were used to push the 15 kilogram box. It's something you should practice. We, on the other hand, are going to move on, because I'll leave that for homework. Let's take those two boxes and use them here. So we have a 5 kilogram box that's going to be hung off the table, and the 15 kilogram box is on the table. This is what's called a modified Atwood machine. I'm going to write that up on the screen here in a second. But this is a modified Atwood machine. This is a super common physics trope. It is on every test somewhere. It shows up a lot. Be prepared for it. We're going to do a lot of modified Atwood machine and full Atwood machine questions. A modified Atwood machine is basically a box on the table and a box hanging off a table. A full Atwood machine would be just a pulley with two boxes on either side. This is a modified Atwood machine. There are so many different varieties of this problem. So many. This is the most basic version there is. Let's continue with the idea that there's no friction. I don't need to make these problems more complicated yet. We'll keep them nice and simple. You built one of these, do you remember?
Yeah.
This was your lab last week or the week before, where you hung the weight off the edge and you allowed the car to go across the table. So you know about how this works. If we were to release the boxes, do you understand how this system would move? Do you? Can you agree that if the box on a table moves 1 meter to the right, will the box that's hanging move 1 meter downwards?
Yes.
Seems like they're connected there. Would you also agree that probably if the box on the table is accelerating, the box that's hanging off the table is also accelerating? Is it likely they're the same acceleration? I think it's very likely, unless the string is stretching, that they're having the same acceleration, the same motion. So I must choose a common direction to call positive. I'm going to call this direction positive. Please notice I'm writing that around the pulley. I always find it's easier to put the common direction for positive near the pulley because it's connecting the two objects together. And therefore, I think it's pretty easy to see what direction is positive for each object by labeling the pulley. Would you guys all agree with that, okay? So, this is a multi-body problem. I think you know what the next part is, the part that you are experts at, right? Draw a free body diagram for the system. That's going to be for each object. And you should go a couple steps further. So I'm expecting you to have a free body diagram for the system and a Newton's law set up for it, because you're going to use a coordinate system that makes reasonable sense. That's all the time I want to give you for this. I'm done. Are you done? Does yours match mine? You should look. It wasn't hard. I didn't do the Y direction on the box on the table. I know it's not accelerating upwards off the table or downwards into the table. I think I can ignore that. If there's no friction, I don't have to worry about the normal force. I labeled this tension T15. It acts on the 15 kilogram box. I labeled this tension T5. It acts on the 5 kilogram box. It's at this moment that we should figure out first whether you guys got these things. Did you get this far? Because if you didn't, you're taking too long. I don't mean that cruel, but but you're going to have to pick up the pace. Remember, you don't have that much time on these FRQs. You're going to have to be able to work at an expedient rate. And none of this was surprising. We've done both of these kinds of problems before. What you should be asking yourself is T15 and T5 the same tension? That's what you should be asking yourself. That's a more complicated question in this problem. And I want you to know you need to be more educated to understand all of the nuance. Because the truth is, they're not. It is how these two boxes are connected. But, and you should pay attention, but I got to go quick. T15 acts this way, which means it acts on the pulley this way. T5 acts this way, which means it also acts on the pulley, but this way. Those two tensions act on the pulley. These are equal and opposite, Newton's third law. These are equal and opposite, Newton's third law. The real question is, are these equal? It depends. They are equal if the pulley is massless. Put that in your notes, please. That's the word you're looking for. That's my code word to you. And you'll need to look for that code word. Otherwise, they're not. I'll say it again. Those two forces are equal if the pulley is massless. Meaning if the pulley has no inertia. I said this already once this semester. This is the second time I've said it. First semester, pulleys have no inertia. Second semester, they do, and this will not be true. But if the pulley is massless, these two are equal. So if the pulleys are massless, T15 and T5 are equal. You need to ask that question. It needs to be an addendum in your notes. You need to know to ask that question of yourself. If there's ever a pulley, is the pulley massless? I will do everything in my power to make sure I write that into any question. But now that we've answered that, you should be able to tell me the acceleration of the system. Right now, it's the same problem you already did. It's almost exactly the same problem that you already did. The difference is the external force is gravity this time. And you don't know it yet, but there's something very important that I'd like you to see. So I'm waiting for you guys to write that T equals 15A here. To consider maybe adding these straight down. Right? One of the tensions is positive, one of them is negative. If you do the problem the way I suggest and make the common direction positive, you'll always get one of your forces positive and one of them negative, and they will cancel out if you add the two equations together. 50 equals 15 plus 5 times A. I'm doing that on purpose. Do you see that we're adding the two masses together? You know that you've done the problem right if that's true, but what is the 50 over here? Where did it come from? You realize that's this box. Its weight, right? That's the external force, is the force of gravity on only one box that causes both of them to accelerate. How much do they accelerate? Well, 2.5 meters per second squared.